Welcome to another module in this MOOC on wireless communications. Let us now continue with our discussion on the probability density function or the modeling of the feeding channel coefficient H. We said that if the feeding channel coefficient H is H equals A e to the power of j phi, then the joint distribution of A comma phi equals the joint distribution of A comma phi equals A over pi e to the power of minus a square. We have already found the marginal density with respect to the channel coefficient A, that is f of A equals 2a e to the power of minus a square, and this we said is the Rayleigh distribution or the Rayleigh density. Let us now find the distribution of the phase, that is f of phi, the phase component, and for this I can integrate the joint density with respect to the amplitude A, and the amplitude lies between 0 to infinity, because the amplitude is always positive. So, this is 0 to infinity, integral 0 to infinity of A by pi e raised to minus a square dA. Now, if you look at this integral, I have a e raised to minus a. So, I bring 1 by pi outside. So, I have 0 to infinity. Now, if I multiply and divide by 2, I have 1 over 2 pi 2a e raised to minus a square dA, and integral 2a e raised to minus a square is minus of e raised to minus. So, this is 1 over 2 pi times minus e raised to minus a square between the limits 0 to infinity, and this you can see as basically 1 over 2 pi as minus e raised to minus a square between the limit 0 to infinity is 1. So, therefore, the distribution of the phase, so we have f of phi equals 1 over 2 pi between the limits for the phase, we have minus pi less than phi less than or equal to pi, which means this is a constant and this is the uniform density. So, if you look at this, this is the uniform distribution, and therefore, if you have the limits minus pi, if you have the between the limits minus pi to pi, this has the amplitude, this has the height 1 over 2 pi, and this, as we said, is the uniform probability. So, the phase is distributed uniformly between the limits minus pi to pi. So, this is a uniform distribution, and therefore, we have derived both the marginal densities, that is both the distribution of both the amplitude of the Rayleigh fading channel coefficient and the phase of the Rayleigh fading channel coefficient, and therefore, f of A equals 2a e to the power of minus a square, and f of phi equals this equals, well, and this is within the limits 0 less than equal to a less than equal to infinity, and this is between the 1 over 2 pi between the limits minus pi less than phi less than or equal to pi. And therefore, now we have the, so these are the distributions, the densities of the amplitude and the phase. That is the amplitude A and phase phi of the wireless channel, and these can now be used to characterize derive various properties of the wireless channel. And further, before we proceed further, let us look at one other interesting point. If we look at the joint distribution of the amplitude and the phase, remember the joint distribution is given as a over pi e to the power of minus a square. I can write this as 1 over 2 pi times twice e to the power of minus a square, which is basically equal to f of the marginal density of with respect to the phase times the marginal density with respect to the amplitude. So, what we have is that the joint density with respect to the phase and amplitude is equal to the product of the marginal densities with respect to of the amplitude and the phase. So, the joint density is equal to the product is equal to the product of the marginal densities. Therefore, this implies that the amplitude and phase are independent random variables. So, the amplitude and phase of the Rayleigh fading channel are independent random variables. So, this means that these are independent, that is a comma phi, the amplitude and phase are independent the amplitude and phase are independent random variables. And these densities can be used to derive very valuable properties of the fading channel. For instance, let us look at the following example to understand this better. Let us look at the following example. What is the probability that the attenuation of the channel is worse than 20 dB? So, let us ask the following question: what is the probability that the attenuation of the channel is worse than. So, let us look at the following example. What is the probability that the attenuation of the channel is worse than 20 dB? So, what we are asking is what is the probability. So, let us look at the gain attenuation of the wireless channel or the gain of the wireless channel, gain of channel equals the amplitude square, which is less than, which is equal to a square. So, what we are asking, if the attenuation is worse than 20 dB, it means 10 log 10 of a square is less than minus 20 dB. So, the attenuation is 20 dB implies the gain of the received signal, the power gain of the received signal is minus 20 dB or lower. So, the attenuation is worse than 20 dB, which means log 10 of a square is less than minus 2, which means a square is less than 10 to the power of minus 2 equals 0.01, which implies a is less than 0.1. So, the gain of the channel is, or the attenuation is worse than minus 20 dB if the amplitude of the channel is less than 0.1. And now, we know that the distribution of the amplitude f of a equals 2a e to the power of minus a square. Therefore, the probability that the amplitude is less than 0.1 is basically equal to the density integrated between the limits 0 to 0.1. So, this is 2a e power minus a square integrated between the limits 0 to 0.1. Integral 2a e power minus a square is minus e power minus a square integrated between the limits 0 to 0.1. So, that is basically equal to 1 minus e power minus a square minus 0.1 square minus 0.01, which is approximately equal to 0.01. So, the probability that the attenuation or the probability that the attenuation of the channel is worse than 20 dB is 0.01. So, this is the probability. What is this? This quantity that we calculated here, this is the probability that attenuation is worse So, this is the probability that the attenuation of the channel, the wireless channel is worse than 20 dB, that is 0.01. So, as we have seen, these probability densities or this model that we have developed for the fading channel coefficient, that is the joint distribution of its amplitude and phase, and the individual distributions of the amplitude and phase components are very important tools. They help us characterize the channel statistically and derive valuable inferences, derive valuable statistical properties of the channel from these these distributions of the amplitude and phase components, and hence these are also going to be important when we look at characterizing the performance of the wireless channel in various scenarios. So, this concludes this module and we will continue in the subsequent module. Thank you very much.